Hello, everyone, and welcome to Singularity One-on-One. Singularity One-on-One is a podcast feature of Singularity weblog, where you can go and listen to it or download it in full. As you already may know, my name is Nicola, aka Socrates, and as always, I will be the man with the questions. Today, my guest on the show is Dr. Randal Koene. Randal is one of the co-founders of Neuroengineering Corporation and carboncopies.org. In addition, he's also one of the associates of Halcyon Molecular. So without further ado, let me welcome Randal to Singularity One-on-One. Hi, Randal.
Thanks.
We're very happy to have you on the show today.
It's good to be here.
Fantastic. So let's begin with the first question. Randal, can you tell us how did you get interested in nanotechnology and neuroengineering?
Oh, that was a long time ago. I was only 13 years old or something like that, and I had so many hobbies, so many things I like to do. Everything from writing and playing music, making music, anything. And after a while, it gets to the point where you realize that you just can't do everything. You realize that we're limited in our capabilities, we're limited in the time we have available, and that sort of irked me, and I thought, well, what would you need? You'd need more time and more capabilities, so you need to enhance yourself, you need to expand your life, and how could you do that? And it so happened that at the time I read a book by Arthur C. Clarke. It was entitled The City and the Stars, and in that book there is a group of people that live in a city called Diaspar, where there's a giant central computer, and they get 1,000 years of life, and then they have to go back in the computer for a while, and then they get another turn later on, so that everyone takes turns. And I thought, okay, so maybe it's true. We're just information. Maybe we can just put that in a computer or something like that. And my dad is a particle physicist, so I thought this has to be physics. You need to decompose someone, put them in all that in a computer, all that information, and then recreate it from the bottom up, which is kind of what the ultimate dream of nanotech is, to be able to manipulate on an atomic scale and put everything together from the ground up. And then, of course, there's this whole problem of thinking and being and what are we, and it's in the brain, so there's the neural engineering part. And later I realized, as I was going through my studies, I started in physics, that, okay, maybe I'm tackling the problem the wrong way because I'm going at it by trying the hardest thing first. Maybe I should just be concentrating on the mind, since what are we, right? You don't really know anything much about what's going on except for what you're processing inside your mind right now. You're processing sensory information. You don't even really touch objects because the atoms never actually touch. There's mostly space in between there. There's an electrical signal that travels up your arm, and you don't even know about the electrical signal either. All you know is how it's being processed in your mind. That's what you sense. And you've got memories and executive function and drives, and all of this together is really what you are. So I decided to concentrate on that, and that's how I ended up doing computational neuroscience and neural engineering. And yeah, that's where it all came from, and this was way back. And yeah, in 1994, that's when it became more formal. That's when I started working on the mind uploading research group, which was what it was called back then. It's a bit of a vague term, but yeah, 1994.
So what is so fascinating about, first of all, what is so fascinating about the science end of it? Like the fact that, as you said, you never touch the world around you. It's mainly space in between, atoms. And you mentioned the electrical signals and so on. What is so fascinating about this?
Well, it is, to me, it's really fascinating that you can have something that is basically a model. It's basically a model we build inside of our own heads, of the universe and of ourselves in it. And it's a representation. It's one of many possible ways that you could represent all of the different interferences that somehow in the end affect our thinking. It's just the inference between all those different atoms and how they interact with one another, forces that are happening. And all of this together somehow, that, photons, pressure and sound waves, all of this gets translated into one coherent model, and that's our life. That's what we are. This is where we are. And it could have been something else. It could have been that this would be processed completely differently. And in fact, We don't know if other species, like take insects, for instance, if they have a completely different type of internal representation, and if that experience, I mean, obviously they're very small brains, so the experience is quite limited and different anyway compared to ours. But even just in the way that it's shaped, it can be entirely different. And I find that really fascinating, that this is what we ended up with, this sensation of being.
So let me challenge you here on one of the points you made. You said that we're able to create a model of the universe. But does that mean that we should also be able to make a model of the functioning human brain, to make a model of our intelligence, to make a model of who Randal Koene is?
When you say we should be able to make a model of it, I'm not exactly sure what you mean by that, because when someone comes up to a neuroscientist and says, well, do we understand the brain, or do we understand this part of the brain? The neuroscientist always answers no. And they do that because even if they've studied the neurophysiology forever, and they've looked at the way that all the neurons interact with one another and what kind of synaptic channels are there and exactly what the action potentials look like, okay, great. That's a way of representing what's going on at that level. But what the person asking actually wants to know is usually something more along the lines of, do you understand why, when I'm thinking this, why it works out that way? Do you understand the strategy that the mind is using? Do you understand that strategy at multiple levels of the hierarchy of how it all decomposes until eventually you get down to the neurons? And then the answer is, of course, no. We totally don't, because we don't know how to combine this large-scale, high-level abstract stuff with that low-level, simple stuff. So that's why the neuroscientist says no. Now, when you say, can we model this in our minds? No, I don't think so. I don't think that we can take all of that detailed information at the neuronal level and we can somehow build that construct as it goes up to an understanding of what it actually does, what the strategy is, and hold all of that inside of our minds. No. But what we can do, because what we're doing all the time is simply interpreting information that's coming to us and combining that with our memories and our understanding, we can use the computation that's happening outside of us and the rest of the universe to improve what we understand or how we can operate in that universe. So for example, I can build a computational model, a computational version of a brain outside of myself, in a computer, in some other operating environment. And because it is carrying out computations, it's carrying out interactions between elements, the results of that I can use, I can interpret. So it's not that I'm building an entire model of that inside me, but I have a model then of the universe that includes in it the understanding that there is a box over there that has a complete model of a brain in it. And that tells me things and I can test it. I can ask it questions and get answers back and things like that. So no, we don't build the model inside of us, but we build something else. And then our interaction with that becomes part of our universe model, our idea of where we are, how we're existing, the feeling of being.
So what does this say then about the possibility of mind uploading? How realistic or unrealistic is that? I mean, if you're saying that you do not believe that we could ever be able to replicate the internal structure, the neural structure of, say, Nikola Danielov here, how are you ever going to create a mind upload of Nikola Danielov? And is that feasible at all?
That's a misunderstanding. I didn't say that we couldn't make a replica of the neural structure of your brain. Why not? We could make a replica of all sorts of things, right? It's just that I was saying, when you said, how do we make that a part of our model of the universe? I'm saying that the model of the universe that we hold inside of our own minds is not one that contains detailed information about the location of atoms and things like that. It's an abstract representation. So of course it won't contain that model. But other devices can contain those models, and they can contain them very precisely. So yes, I do believe that you can do that. In fact, I don't see any reason why you couldn't. I mean, why shouldn't you? If it's a machine that is basically, it's a biological machine that's carrying out processes that cause the activation that we can see when we look at an fMRI, for example, and the propagation of this activity, then you could make another device that can produce the same types of patterns of activity and their propagation, etc. So yeah, you could do that.
So that was my misunderstanding, and I apologize for that. But let's see then. Sorry, I have a horrible headache here, and I'm just trying
Oh, sorry to hear that.
to connect.
Were,
I'm not
if,
connecting well. I apologize, which is kind of funny when we're talking about it. My head is like
yes,
bursting.
I know. I was just thinking if you were actually a whole brain emulation right now, then you could probably just see where that pain was coming from and sort of tune it down or turn it off without using drugs. But
That's
that's just,
That's
yeah.
fascinating. So let's grab that point then. So say Nick Danilov here has a horrible headache and therefore is unable to conduct a proper interview, but you have the ability to create a replica of my mind by uploading it to another substrate, which
Hmm.
then in turn can conduct the interview for me
Yeah.
while I go and take a break, for example.
Yeah, absolutely. Why not?
How crazy is that as a possibility? Is that science fiction entirely, or is it a possibility that you see happening?
No, it is not science fiction. It's science. It's not science that's here tomorrow, but it's also not science that's here 2, 3, 400 years from now. I haven't. Okay, so there's a number of publications that I've been writing up recently, and it so happens they're all going to be showing up somewhere in early 2012. And they're about the actual projects that are currently ongoing that relate directly to the sort of things that need to be done to do whole brain emulation. And these are the sort of things that, while we can't tell exactly how many hurdles are going to be in their way, so we don't know if it's going to take 5, 10, 20, 30 years, it's pretty sure that when you look at the type of project they are and the fact that they depend on today's knowledge, today's science, and today's engineering, that these are not things that require some sort of magical ingredient that we need to wait for a couple of 100 years. It's not science fiction at all.
So, what are the main approaches to create a whole brain simulation? I mean, I've seen a number of people who are attempting to do so. One of them is Dr. Henry Markram. Another one is perhaps, I think, IBM's Dharmendra Modha.
Dharmendra Modha. Yeah.
Yeah, Dharmendra Modha. So, is there a difference between their approaches and your approach, and how
Yes.
do you go about creating a whole brain simulation?
Yes, there's a big difference. And the difference popped up when you said, well, when you started talking about a whole brain simulation. See, that's actually what Markram is doing. And Dharmendra's project is an entirely different project. We can talk about that separately. But if you look at the Blue Brain project, where does the information come from that's going into that project? They're taking a bunch of different animals, lots and lots of rats, and they study in them things like what is the average, what is the distribution of distances at which a neuron branches, a typical neuron in some layer of the neocortex will branch, and how does it connect to other neurons of different types. So they get a huge database of statistical data. That statistical data allows them to build a composite model. This is a model built up of information taken from thousands of animals and lots of different studies, and it's probabilistic. And then, after they've built the typical structure of a cortical column, then how do they set the connections in there? They set them according to these probabilistic tables, and they give them some weights that seem reasonable, and then they can run simulations on there where you see oscillations that are typical. Those oscillations are largely dependent just on the duration, where how long a neuron cannot spike after it is spiked. So you've got this after hyperpolarization, and also on recurrent loops that exist in the system. And you can see the propagation of activity in a sense that you would expect to see in a rat if you just looked somewhere in that cortical area. And that's great, and you can learn an awful lot from that. But what do those synaptic connections really mean? They don't actually mean anything, because these are not the connections that came from a rat that had a certain experience and maybe learned its way through a certain maze. You take this model and you put it in the maze and it's not going to know what to do because it's not that rat and it didn't set those synapses that way for a reason. You can train the simulation to do something, but again, there's a big problem there. You've got a huge system with lots of neurons, lots and lots of synapses. It's what we call over-parameterized. It means it has so many parameters. There are a multitude of different ways of setting those up so that it will achieve the task that you're trying to get it to do. But there's no guarantee that that's exactly the way that it is in any particular rat. If you take a comparison, let's say we had a computer program that's supposed to produce one type of output, like let's say it's supposed to calculate some sum of different numbers or some equation. You could implement that in one way, and you could have 50 other implementations of the same type of program, and they produce similar results, maybe not exactly the same, and they go about it in all sorts of ways. And then if you're doing the simulation approach, basically what you're doing is you're sampling from each one of those, learning a bit about it, and then making a 51st copy that's slightly different than all of the other 50. And it produces some result that's somewhere in the range of what you expect. Now, an emulation approach, whole brain emulation, it would be take one of these programs and copy it line for line so that it produces exactly the same output. And that is what the difference is. So you need tools that actually acquire the data from a very specific brain, from one individual rat or human brain. That's the difference.
So in your case, you're looking at creating an exact copy, and in the other case, basically you create a probabilistic, would it be fair to say a statistical model of a basically average rat or average human being,
Yes.
but not any existent individual.
Yeah, that would be fair to say. And I give it the shorthand separation by just calling one thing a simulation and the other an emulation, because we know the concept of emulation from computer programs where, let's say, you have a PC emulator that you run on a Macintosh, and then you hope that all the programs you're running on your PC run exactly the same way in that emulator. That's where that comes from.
I see. Yeah, that's a very important distinction indeed. So, so perhaps now is the time to go a little bit more into the details of your work. Should we start with Halcyon Molecular? How does Halcyon Molecular and your work there fit within your overall goals?
So as I said, there are a few details there that I can't go into, but I can give you a general outline.
Absolutely.
So I'll start with a little historical bit. I was not initially planning to work for a sequencing company. What I wanted after working for, basically after starting a neural engineering department at a nonprofit in Spain, I wanted to go and work for a company that was really involved in doing circuit reconstruction in the brain. And so I was looking into, for instance, working for the startup Brain Corporation that Eugene Itzkevich started in San Diego. And, well, that wasn't quite the fit. So I decided to look elsewhere. And I discovered that Halcyon, well, they approached me and asked, hey, would you like working here? And I thought, well, why would I work there? It's a DNA sequencing company. And then I visited them and I found out that there's a lot more to it. They're really interested in the long-term future and in what they can do when they have this tool. So they want to use this tool as a revenue source that they can use to start other very interesting projects that are heading towards curing disease and towards extending life and towards artificial intelligence and various other projects. And they're also interested in using the tool to acquire data that you would want to get, for instance, out of a brain. Say some of the most modern approaches to collecting information about all the connections in the brain, the connectome, is one of those that is being proposed by Anthony Zador, who works at Cold Spring Harbor Laboratories. And it involves building DNA barcodes that are specific for every neuron in the brain, and which would be delivered to the synapses between them. And then when you pluck out that information, you pluck those barcodes out of those synapses, basically, and you sequence them, then you know it's basically like pointers that are pointing to each other. Then you know this neuron is connected to that neuron. And that requires an enormous amount of sequencing of DNA, which is why, say, the tools built here, a high throughput method of DNA sequencing, that's exactly the sort of thing you'd be looking for. So now we have a tool that's actually applicable to the problems I'm interested in, and you have people who are interested in putting their work and their finances and their future profits into things like what I'm interested in. And it turns out that they're a fantastic bunch of people. So it was mostly that, actually. It's the people that drew me here. And so that's why I work for Halcyon.
And how is that different or similar to the work that you do with carboncopies.org or the work that you have done previously in Europe or for Neuroengineering Corporation of Massachusetts?
Yeah. Well, I'll start with the work that I was doing in Europe. The work there was, it looked like a very promising job because I was offered the opportunity to start up in my own department and to hire whomever I wanted to hire for it. And the only requisite was to come up with interesting neural engineering problems and solve them by, for example, building neural probes that would eventually become patentable or profitable in some way. But there wasn't a very short timeline on that because they had a great financing system set up for the next 10 years. Mm-hmm. Then, unfortunately, the financial crisis hit Spain. And the investors, they got a little worried and they wanted really quick results, which changed the type of project they were interested in. Mm-hmm. To the point where it really wasn't that interesting to me anymore. Mm-hmm. So it was a really great opportunity, but it just didn't pan out that well. So in that sense, it wasn't meant to be that different, but it just didn't turn out that well. Carbon copies is a different matter entirely. Carbon copies is something that Suzanne Gildert and I set up on purpose as a place for pulling together the network of people and the knowledge that is necessary to build a roadmap towards whole brain emulation. And it's really done quite a lot of that, actually, because we do have a very extensive network right now that reaches to just about everyone who's involved in the most cutting edge work in the field. And we're putting out, or at least we will be in 2012, putting out a lot more fundamental information about it so that everyone can read the details of what is this actually and how does it work and how would it work, what is actually going on, what are the projects that are going on in that area. So it's a nonprofit, which means that people don't have to worry about are we associating ourselves with a certain company, what's going to happen to our data or things like that. I think that's a benefit when you're trying to build a network like that. So I thought that building a nonprofit like this was a better idea. And yeah, that's a large part of my effort, actually, keeping that going.
On your website, it says that you're basically looking into practical approaches toward what you call advanced substrate-independent minds, that is transferring mind functions from the biological substrate to another substrate. So how far along that goal have you managed to get so far?
First of all, I'd like to say that we actually just call it SIM now. We call it Substrate Independent Minds. We used to say advancing in front of it, and that's still on carboncopies.org because we wanted to make sure that it's clear it's an action-oriented organization that's trying to advance this topic, not just a discussion hub or something like that. And you're asking now, so how much have we advanced on this topic?
What are your benchmarks towards accomplishing that goal, and how far off in time are we looking here? Are we looking a decade, 2 decades, and which are the short-term goals that we need to meet so that we know that we're making progress?
Okay. So some of the results that we've achieved so far is that we've put together a roadmap that contains information about what is required to do a substrate-independent mind, which are the different routes that you can take. There are a few major routes that you can approach it by. What projects or what sort of projects would provide the tools necessary to fulfill the requirements of any one of those particular routes, and then to connect with that the people who are working in those areas and to discover key pieces that are missing, parts that nobody's really paying enough attention to and what needs to be done there. In the last year, there's been an increasing interest from high-profile people in neuroscience, such as Ed Boyden, to also look into brain circuitry, and how would you replicate it, and how would you acquire the data for that. And so we have started some early collaborations on developing technology that can actually acquire data at large scale and high resolution. And it looks like this is giving us a very good picture, at least along one of the directions towards substrate-independent mines, namely the whole brain emulation approach, this very conservative approach, and what it needs in terms of structure and in terms of function, and then tools that can acquire the structure and tools that can acquire the functional characterization of components. So this is very clear, and that gives us a really concrete project for whole brain emulation, at least for that approach to substrate-independent mines. As far as milestones are concerned, we're still finishing up some of the fundamental literature so that we can put that out early in 2012. Then along 2012, I think it's time to do the first projects on the large-scale data acquisition from the functional characterization, for the functional characterization of components, because that part's been neglected somewhat. That's basically one of those key areas that needed more attention. Meanwhile, to also support the ongoing work by people like Ken Hayworth, who've been doing the structural side of things. And then hopefully after 2012, we should at least have a very early prototype that shows that the kind of tools we need are available in both of those parts, so structural and functional. And the hope is that knowing that and being able to demonstrate that it will spur the kind of investment that's necessary to build these on the scale and with the kind of precision that's necessary to get so much data, to get all this data that you would need out of a brain. Now, how long will that take to get to that final result? That's a really hard question, because it depends so much on the resources that you get. It depends so much on how much people invest and whether they, really put a lot of people on the job, or if a lot of scientists pick it up. So yeah, I've tried to display this on a graph that I showed during my H+ talk in Hong Kong recently, and it was a quick graph just to show that the connection between resources and when would it get done. And so I always hope that people will put in so many resources that it can get done within the next 20 years. But maybe I'm being optimistic, maybe not. We'll have to see. It's also therefore a matter of advocacy. It's a matter of telling people, look, this is a concrete project. This is not like, let's say you want to try life extension and you want to do it the biological route, and then very often somewhere someone says, oh, and to do this, we have to understand biology. They just kind of say that, understand biology. It's like, oh, wow, but that's a really big topic. Or even if you had a topic where it said we have to understand neuroscience, that would be really huge. But this isn't, because whole brain emulation is really conservative. It says we're assuming here that what we are is an emergent function of what's going on at the bottom level. And the bottom level we've studied for many years. We know, even though we don't have catalogs of everything that's there, we know how to get that data if we need it. We know that if we need a parameter about a certain type of synaptic channel, we know what kinds of tests to do to acquire that data. So what we need now are tools that can do this at large scale and high resolution. So it's a matter of applying our knowledge, our scientific knowledge about how neuroscience works at that level today, together with the engineering that is required to build the kinds of tools that can get that data. It's a data acquisition problem. It's not a huge scientific problem. It's not a maintenance problem. It's not how do you keep this car running forever or something like that. In that sense, it's very concrete, and it's about how many resources.
So let me ask you about the detail, to get a little bit deeper about what we do and what we don't know. Let's take me, for example, and let's see if this question will be outside of your field, but I suffer from migraine occasionally, and on some occasions it's pretty serious. So I've been to the doctor a couple of times. We've done fMRI scans and a couple of other tests, and so far they're clueless. They have no idea what could be the reason. One theory was that I might have sinusitis, which turns out I don't. My eye prescription is accurate because I wear contact lenses, but I get the headaches not when I have my contacts off, but when I have them on too. Therefore, that's not related to that either. And the fMRI did not seem to help them in any way possible to come up with a diagnosis. So let me ask you this: doesn't that show that there's still we're very, very far away from any practical results? One, and two is, what would be the dream outcome of us getting to know pretty much everything that there is to know about the issues and the problems and the neuroscience that's happening right here?
Yeah. I think that's another point that really needs to be made very clearly. One thing is to want to understand the brain fully. The other one is whole brain emulation. They're not the same thing. Even if you make an emulation of a brain, a complete emulation from the ground up, and even if it works, it doesn't mean that you have a complete understanding of the brain. Not automatically. It will make it a lot easier to get that understanding because at least you have total access to every component while it's functioning, and you can see what's going on, and you can turn it off and turn it on, test, does changing this change anything? So it will allow exploration in a way that we've never been able to do before. I like to call the idea a virtual brain laboratory in a sense, and everything can be backed out of. So instead of trying a drug on some people and saying, well, let's see if it has any adverse reactions, if it does have adverse reactions, you can dial it back. Mm-hmm. So those are huge advantages if you're going to do any kind of medical research, if you're going to do scientific experimentation, but it's not an automatic outcome. Because as I was saying before, there's a difference between this low-level understanding and giving that answer, yes, we understand the brain. We know at every hierarchical level how this strategy works. And you're right, there's a big difference there. But I see those kinds of things, like being able to use it as a virtual brain laboratory, also as some of the huge advantages if you make these kinds of models. And that doesn't just happen when you're doing whole brain emulation on an individual level for a person because they want that, but also if you're just doing brain emulation, brain circuitry emulation of, say, regions of the brain or of animals, smaller animals where you can test things. This is some of the reasons why many of the neuroscientists who are now coming on board with the really exciting human connectome project, so this idea of getting all the connections from the brain, and brain emulation, so brain circuitry reproduction, like the kind of things that Ed Boyden's interested in, they're coming on board because they know that is what we need now. We're done just looking at very small scale stuff at high resolution or taking fMRI scans where all you can say, oh, yeah, there's activity in that part of your brain when you're thinking this, but what does that really explain, right? Okay, so it had to happen somewhere, right? The activity had to be somewhere. You need that connection between the two, and that means you need to do the kind of detail that you're usually doing at the low level, but at a very large scale, the kinds of populations of neurons that are actually involved with these kinds of functions in the brain.
So in a way, the whole brain emulation will be a step towards the basically a step in the direction of learning more about the brain itself and diminishing that area that we don't know what's going on.
It would certainly help, yes. Yeah.
And what would be the dream outcome of your work, say 20 or 30 years down the road? What would be the best case possible scenario that you can dream of and that you are waking up every day with a smile on your face and you want to accomplish this? What is this? How does it look like?
The dream outcome is an in vivo method of carrying out an upload to a whole brain emulation so that you have a substrate independent mind. And knowing that it works, so having it validated. A validated in vivo method of doing it. Like, post-mortem methods are interesting, but in vivo would be really my dream.
So that's fascinating. So let's try and break this best case scenario in parts. So first of all, what's the big deal? Why should we want to upload our minds to begin with? What's the benefit of doing so?
Well, there are a number of them, and I try to outline them, for example, in the paper that I posted on Kurzweil AI, pattern survival versus gene survival. And there's going to be more in some of the other writings that are coming out in 2012. I have a contribution to the book, The Transhumanist Reader, and one that's coming out in the book called, I think it's called The Singularity Hypothesis. Not that I personally attach a huge amount of value to either of those labels, but I thought it was a good opportunity to try to write about the reasoning behind substrate-independent minds. Why is it important? Why would you want it? What's it good for? And of course, a lot of people who are looking at this see this as a way of potentially living longer. So, okay, if you can actually transfer your mind, yourself, as you are, into some form where it can be backed up and can be fault tolerant, can exist in many places so that if something happens in one place, you're still fine, and all of this stuff, great. It could help extend your being, your sense of being, your life. But there's more to it. I mean, if you look at the bigger picture, actually I should look at two sides of it. Near-term big picture, long-term big picture. Near-term big picture, look at all the other methods that are extending our lifespan. Most of those methods treat it as a problem of keeping the body going and don't really worry too much about what the mind will be doing when we're 200 years old. But even if you have a perfectly healthy elderly person, say someone who doesn't have Alzheimer's disease, what would they be like at 200? Would they be just like a 16-year-old? They obviously wouldn't, because they've experienced a whole bunch of things. And that's a great thing. That's wisdom, right? You've experienced a lot of things. But it also means that you're building a filter. So take a slice of tissue from a baby. You see that there are still many connections being formed. Take a slice of tissue from someone who's 14 or so, and then you find that there are a huge number of connections. And then take an adult slice, and you'll see there are way fewer. And it's not surprising, because a lot of things have been pruned, don't get used very often, and other bundles strengthened, which is very useful because it means that you react faster, you have instant recognition of things that are familiar, and you deal with them in a familiar way so that you have automated ways of dealing with all the problems in your world. But these filters mean it's very hard to accept entirely new kinds of thinking, new approaches to things, which is why we always struggle with a generational gap. And you can imagine that if you're 200, that becomes even more so. So you're still totally there, you're cognitively active, etc., but you always see things through this particular filter. Meaning that even just living longer is actually cause to deal with problems in our abilities, in our mental abilities, in our capacity to deal with information. So we do need to look at that, even if you're just talking about some relatively short-term extension of life. Now, in the long-term picture, we have all kinds of challenges ahead. What we are right now is something that has been evolved to help our genes survive on this planet, in this environment as it is right now. That doesn't mean it's optimal for all other challenges that are coming up. It doesn't mean that we understand the challenges that may be coming either somewhere else in the universe. I mean, we can't even take off our spacesuit on the moon, right? That destroys the environment in which this body lives, in which that mind works. So that doesn't work. We can't actually sense the moon. We can't really experience what it's like because we're always breathing our own refiltered air inside that spacesuit and whatever. Yeah. So there's that. And then there are other challenges we can't even imagine right now, where you need to be able to think differently, where you need to process different kinds of input, and where you need to compute in a different way to really be able to deal with those challenges. And some of them may even come from our own creations. Imagine that we produce machines that have really good thinking capabilities, and their capabilities may in many ways outstrip our own. A calculator already outstrips mine when it comes to doing precise calculations. And I can't even imagine what it's like to think with quantum computation. And those sort of things are the kind of challenges that I would like us to be able to continue meeting. I think that the reason why we feel we have some control, some limited control over where we're going, is because we're currently the most intelligent, dominant species on the planet, and we can sort of coordinate that between one another. We keep each other in check too. There's a balance of power going on between these 7 billion people, where sometimes you have someone who goes off on a crazy spree of dictatorship, etc., but they eventually get brought under control. Now, if we were not, let's say there's something else that's more intelligent than we are, then our situation becomes a lot more like the situation of the other species on Earth, where maybe we don't mean them any harm at all. It's just that we have completely other goals. It's like, it's not that we want to take away the livelihood and the environment in which gorillas really like to live. It's just that, we have other uses for that land. We have other ideas in mind of what we're going to do with that. And that could happen to us. And basically, we're no longer in control of where we're going at that point. So if you want to stay on top of that, if you want to meet all these future challenges, you need to be much more flexible and adaptable. And I think what that means is we need to take charge of the adaptations that we can carry out, the adaptations of ourselves, our ability to grow not just in terms of taking in experiences, but grow in capability as well. So we as a species can continue to grow. I think that's one of the main things that substrate-independent minds tackles and dares to address, that a lot of other thinking that goes on in related communities where it's about life extension or artificial intelligence and such don't really go into. I mean, maybe the closest is the brain-computer interfaces, those interests, and neural interfacing. And that's also very closely related to SIM, actually, so that's not surprising.
So say that the process of mind uploading is in the very last step of towards its completion. How do we go about verifying whether the sort of the whole brain emulation is an exact copy of the original, as you said, in vivo?
Mm-hmm. That is actually the reason why I said in vivo, because there are some really interesting proposals about how to do the development of a whole brain emulation post-mortem by taking a brain and slicing it very thin, reconstructing it in 3D, and correlating the components you find in there with libraries of components that have such morphology and distributions of parameter settings. This is basically the approach with the automated tape collecting the automated tape collecting lathe ultramicrotome, the Atlam. But the approach is dangerous from an engineering perspective, because it's very difficult to correct for systematic errors. Random errors, the brain itself is relatively good at dealing with because it's robust. You can have all sorts of brain damage. You can have all sorts of neurons dying from, I don't know, alcohol poisoning or something, and you can still function. You have a distributed network there. But if you have a systematic error instead of a random white noise type of error, let's say that while you're scanning, you always measure dendrites 1 micron too thick or something like that, then these might be things that if you don't notice them and you don't know how to compensate for them directly, they just show up in your result. And that's that. You press the big green go button and it's an entirely different functioning mind than you imagined. This is where combining structural scanning and doing in vivo functional work really comes in. You need that second dimension of information where you're providing validation, where you can say, okay, so this is what we have here. This tells us a lot about how it's connected because it's giving us the structure. And at the same time, we've measured the kind of function that this component has, and we know how it operates together with the others when they're all operating together. So we can check if our model is doing the same thing. There's a little more to it that I could get into as well, because there's a problem of missing latent function when you're doing functional scans. There's a problem of what I just said about the errors in the structural stuff. But, and of course a one-to-one mapping that you'd have to have in structure to some function. But just to show what I would actually prefer as an engineering approach is not one where you build the entire thing and then press a green go button. It would be much better, in my opinion, if you can replace bits and pieces at a time and test whether they're still operating correctly. You could even test them in parallel. You'd have the same input going to the actual neurons and to the artificial ones, and see if the network you've produced produces the same output within some error margin that, because not even a biological network produces exactly the same output for the same input all the time. It doesn't work that way. But you want it to be within a certain margin. You want to see whether it still works within the whole. So you want the whole to be alive and to be functioning so you can see whether this replacement is okay. That's kind of the same that you would do for any neuroprosthetic or for any prosthetic in general. And then as you go, you eventually build something that works and is validated. I would prefer that approach. I find it much more comforting from an engineering point of view.
So let's say you have created something and it has been validated, but then what happens from that point in time onwards? You have the original and you have the whole brain emulation. Mm-hmm. How do you treat each of these? Do you have to destroy the original? Do you give the quote replica or the copy the same rights that you would give the original? Is there some kind of a, I don't know, hierarchy between a second generation copy and a third generation copy of the copy?
Well, from our perspective, I think a lot of the things you can already sense just by saying them, that they don't make a lot of sense when you say them, right? Like this whole hierarchy of, who's more valuable, what do you base that on? Let's start with, is it really you? Which is really a question that comes up a lot. And the interesting thing is it depends on at least your philosophy. So first of all, it depends on what you think is you. This is not very easily solved. You can look at a lot of the work by David Chalmers on that, that it's not entirely clear whether you need to worry about continuity. So does there have to be a continuity between your biological self and the replica that's operating? Or is it completely okay to just put a huge separation in there? You build this entirely separately somewhere on the side and then activate it, and then it's you. That's not entirely clear, and I was a fence sitter on this for a long time, and I've gotten a little better because I spoke with Max Moore, who gave me this. He did a thesis, so basically on personal identity, and so he looked at all of these aspects. And one of the interesting things that he came up with is that it's really not so much about the process that you use or the procedure. It's more about how abrupt, how much are the differences, because you yourself are now not the same person that you were when you were 5 years old. The reason why it is still you is because it's been a gradual change. It's not suddenly going from 5-year-old you to tomorrow it's you who you are now. Those would be completely different people. So it's about this gradual nature. If you made a whole brain emulation and it woke up in a black box and it had no sensation and everything was suddenly different, this could be way too disruptive. That you might not want to consider that you. If basically nothing seems different and you're waking up and you look around and, hey, oh, okay, so that worked, then there's not too much change all at once. So this is more the direction I'm taking right now in my view of personal identity and continuity of self, though I still do worry about whether the process matters, because you can imagine doing something like whole brain emulation in many different ways. So you could build the replica entirely separately, or you could do an in-place replacement of one neuron at a time. And those are different, because in the case of the replacement in place, there's never a moment where you get turned off and on, or where it's very clear that you're just suddenly making this new physical entity. So they're different in procedure. Then you asked, is it okay to turn off the biological version? Well, again, I guess the procedure matters there a little bit, because you might not even have that option. But I don't see any reason why you would. It's kind of like, okay, so even if they both are you to begin with and then start experiencing different things, which is fine, it's just you going in different ways you could go, right? Like we all have different paths in life that we could take. Why would one be less valuable than the other and it'd be okay to turn them off? I don't get that. It's like, it's like two people or twins. Why would you kill a twin? It doesn't make any sense.
But the issue is for example, if I have a mind upload and the original is still in existence,
Yeah.
which one of them is my wife's husband legally and practically?
Yeah.
And if the original disappears and there's 2 or 3 or 4 uploads of me, identical copies of the copy, which one is the one?
Yeah.
How do we differentiate between them? If I have kids, which one would be their father? If I legally place my upload to be my heir, which one would be the heir? All those sort of maybe paradoxical and crazy, but in a deep sense, ethical issues, I think are very important. So that's actually the angle that I'm coming at it from, because I'm not a scientist. I don't really care too much about the technical end of things. For me, the more important questions are why rather than how, why, and then so what.
Mhm.
So what is like the biggest
Okay,
question
well,
for
we can
me?
get to the so what afterwards, but we should deal with some of the ethical things that you brought up first and some of the legal questions that you brought up first.
So, for example, Charlie Strauss, I remember in one of my favorite books, Accelerando, raised the question: if a mind-uploaded Muslim eats a virtual bacon, is he breaking the Quran or not?
I would say yes.
But
I
that's
mean,
not really bacon because it's not coming from pig. You see, it's
no, it's all in
virtual.
the definition of really. It's like so many things in any scripture. You need to decide how you're going to interpret it, and then you can base your answer on that. That's part of the problem, right?
And
One
then
of the
if you
things,
delete a copy, is that a murder?
again, it's a matter of how you look at these things, and yeah, we have to deal with that as a society. The thing that I find so interesting about so many questions related to new technology, including this kind of technology, is that very often it gets approached as if it's some really new thing that we've never faced before. We've never faced these kinds of questions before, when in reality it's just another variant of questions that we've dealt with all the time. So, for example, the matter of death and is it okay to kill someone? In the past, that really used to depend on who they were and what their position in life was. Like if you were a nobleman and a peasant offended you, maybe it was okay to kill them. And if you had a slave, that was an entirely different matter too. Sure, it was, destruction of property, but it's not the same thing. Now we've evolved from there by changing our ethics and saying, okay, that's not right. We should really treat them all as equal. Everyone has these inalienable rights, etc. And perhaps we can evolve further to look at this also when we talk about people made up of different substrates. Is it the fact that this person is running on some other hardware very much different than them having a different color of skin? Well, you should really think about that. But I don't think that these problems are unique. I don't think that they're that new in law. And all the other stuff about who is your wife's husband. Again, this is one of those things where we can look at some similar precedents when it's about things like polygamy versus monogamy and harems and all these other situations that have existed, and just choices that you make about how you lead your own life. But then, for instance, what about her choice? What if, for instance,
Exactly.
for her, it's not so much about, is this the person that I like to talk to, but I like him to have that body there. Or maybe she doesn't like your body. Maybe she prefers, one of the others. I don't know. The point being, the point being that it also involves her choice, her wants and needs, and so it's a more complicated question on one hand, but on the other hand, it's also a more familiar question because it's really about our decisions, what we think as people and as a society are the correct results. Laws, sure, they should get updated and rewritten and changed as necessary to deal with what we think is right given the new circumstances that we're in. And that happens for everything, for genetically modified foods to uploading. So I don't really see that that's any different.
So let me ask you this then, just continuing along that path of scientific development. Let's say we succeed in creating a whole brain emulation. Do you think that it wouldn't be very far afterwards that we could be able to do the reverse process, which is to say to take that emulation and install it, for lack of a better word, on a clean body, for example, as the
Yeah,
carrier?
I don't spend as much time working on that part of it just because the data acquisition part is already so hard. But I do see that it's very important. And I think that it's definitely the first thing that people will want to perfect as soon as you have some way of doing an upload to substrate-independent mind. Sometimes the body you want to enter will be different than what we have now because maybe you are trying to travel to Alpha Centauri and you'd rather be a spaceship than be a human. But
Or you just want to make your wife happy?
if that's the kind of thing she likes, yeah, okay. But but certainly, and this is actually one of these big questions. People always come to me with, but isn't it going to be a problem that a substrate-independent mind doesn't have a body? And then I kind of wonder why they made that assumption in the first place. Does this have something to do with popular culture or movies or something that's been said about uploading before, which was one of the reasons I don't really like the term. It's very confusing. There's nothing in there that says anything about not having a body. I think that embodiment is essential because we're not just what's in here. So much about the world is being computed for us by the universe around us. Like, even just think about some primitive animal tracking prey. Most of the time, it's going to try to predict a little bit ahead, but it won't compute the perfect path, making a model of what that prey that it's chasing is like and how it's going to try to evade it and things. Instead, it looks and gets feedback about where the prey is now and adjusts itself to that. This is all computation being carried out in that environment by other things, not by yourself. So the input and output is really important.
Yeah, my presumption would be that if we are so sophisticated as to be able to do and successfully complete the whole brain emulation, then the reverse process should be much faster and much easily accomplished than the original process.
That's my assumption as well.
And it wouldn't be too far away from that point.
Yeah.
So you agree with that? That's interesting.
Yes, I do. Yeah.
And let me ask you this then: do you read any science fiction writers that could potentially inform your work in one way or another? Is that a possibility at all? And if you do, who are your favorites?
If I inform my work, as in the things that I could learn from, or that other people could read to get an idea of what's...
In the sense that it could either inspire you, or it could bring to light some of the implications of your work that you haven't considered before, or it could help you come up with new and creative approaches of accomplishing your goals.
Yeah. Well, as you already heard, it all started with a science fiction story. Although, I'd been thinking about things before then, but that science fiction story really crystallized where to go. And since then, I've read quite a bit of science fiction, but in the last, say, 5, 6, 7 years, I've had very little time to do any recreational reading, so there hasn't been as much. But I must say that I have taken out a little bit of time to read some Greg Egan, because I really, really like his work. And so I would suggest that, you can learn a bit about at least what sort of issues you need to deal with and what's going on in emulation when you read something like Permutation City. So that's the kind of place where you could go and look and get some inspiration.
Because I personally have come across Cory Doctorow and Charlie Stross and Robert J. Sawyer and a number of other science fiction writers who have spent a lot of time thinking of the process and the implication of mind uploading. So I thought it would be interesting to see if you sort of... And they raise lots of the ethical and sort of primal questions that could potentially arise in that situation. But we spend enough time on the positive end of things. Let's flip that coin and look at the other end of it. Is there something that you're really afraid of? Or in other words, what's the worst case scenario? What's the potential nightmare result of your work?
Nightmare result of my work, or nightmare result in general of what might happen in the future?
Or in general. Well, you can take both if you want.
I guess we could look at both, yeah. Let me just look at the general one first, which is really comes back to that issue I was talking about meeting new challenges. My main worry is that either we're going to go through a period of turmoil where the economies in the world and the way things work just don't work as effectively anymore as they have done for the most recent time. So that, for instance, just organizing the kind of infrastructure that you need to do futuristic work, to do these kinds of large-scale projects, becomes impossible. So I'm worried that we might be on a limited timer here for getting these sort of things done, because I don't know exactly where things are heading in the world at large. It's always, we don't know exactly. So that's one of the things. Politically speaking, and therefore the sort of fallout that you can get from political issues. The other one is that that the environment in front of us, that the kinds of challenges we're going to meet there, just in terms of something that happens to the environment we live in, or something that happens because of other technology that we develop, such as artificial intelligence or nanotechnology, just to name a few, or biotechnology, think of biological weapons and such, might make the environment unlivable for us, or might make it so difficult to live in it that all we can do is barely scrape by trying to survive without really dealing with bigger problems and possibilities and opportunities. So I worry that we might be causing such issues ourselves, or that something like that may come towards us. So I feel a certain urgency or desire for haste to try to do things that will allow us the kind of adaptability and the kind of security and backup and possibilities that go beyond that. So that's one of my bigger general worries, and that's really why I do this. Well, besides, of course, the just the desire for more capabilities, and basically what I used to call wanting to be able to understand everything and create anything, which is not something you ever achieve, but it's something you like being on a path towards. Now, in terms of the kind of nightmare scenarios I think of from my work, if it were done badly or if someone were not paying attention to problems, I think that they're kind of along the same lines as what we worry about with a lot of information technology today, which is who owns it, what are they allowed to do with it, who's influencing it or changing it, even when you don't want it to be changed or written that way. So how do you make sure that you have some sort of personal in-chargeness about your own information? Like we want to have about our DNA, and you'd like to have that as well in terms of your mind. You have essentially some sort of barrier where you can say, okay, I permit this, I don't permit this. That's the kind of thing I do worry about. And also, of course, that someone may take insights that we gather while we're working in this direction and use them badly. Let's say use them to create something that is meant only as some sort of artificial intelligence AI warfare thing that they use maybe for intelligence gathering or something like that. And I wouldn't want it to become something that is associated with those sorts of issues, but also I wouldn't want to have to deal with it as a sort of an arms race where you try to constantly stay ahead of these possible negative outcomes. So my preference would be to try to predict as much as we can where lie the dangers. So what sort of information do you need to protect, and how do you make sure that there is that you have, what do you call these things now? It's like controls, like that you have on your personal privacy and stuff like that, and similarly that we understand a bit about all the rest of the technologies that are being developed around us and how these may interact. It's dangerous to think of one technology as developing in isolation, as if it's on an island, and that's the only thing that's going to happen, and then predict the future is going to be like this, because that's the technology we'll have. There's all this other stuff going on around it. I mean, if you're building the kind of technology to do this data acquisition for whole brain emulation, what if you use the same sort of technology for something completely different, like some nanotech approach or something with AI?
But that's my biggest concern, is that what we're talking about here would have radical implications. Legal, religious, ethical, political, spiritual, you name it. It would change everything, right?
Yeah.
What about unintended consequences, and especially in the narrow personal responsibility sense? Do you not ever have nightmares of you playing the role of Frankenstein, Dr. Frankenstein?
I do worry. I worry about possible negative outcomes. But this is why I said, okay, are you looking at my worries in the general picture, or my worries about how things may turn out with the work? Because you have to balance the two. Saying, I'm worried that something bad may happen because of what I do, and therefore I won't do it, is not the cure-all to all problems, because A, the status quo isn't necessarily fine. It's not safe. It doesn't mean everything's going to be okay. And B, if I don't do it, who says someone else won't? And if I'm the one who's worrying about the potential negative outcomes, then maybe I should be doing it, because at least I'm taking that into consideration. So that's my view. when I think, should I be doing this? I'm taking those things into consideration. I'm saying, okay, at least I will worry about those problems. And also I see this as a potential way of guarding against other challenges that are coming our way. Because, as I said, this is not happening in isolation. All the other technologies are still going to be developed. People are going to work on nanotechnology. People are going to work on artificial intelligence. This is not going to stop just if you don't do whole brain emulation. The only thing you get by doing sim is that you give us a chance to keep up with all that other stuff. You give us a chance to choose to participate in getting new capabilities and being able to safeguard some of what we are.
So what's the relationship between mind uploading and the general concept of the technological singularity? Where does mind uploading fit within it, in your opinion?
That's a really tough question, and I tried to address that a little bit in the piece that I wrote for the singularity hypothesis for that book. And I think that it's, to me, where it fits in the singularity is us not being a bystander who sees the singularity happen and then just take off, and we're left behind basically still communicating the way we do now and understanding things as we do now, but not being able to understand what those other intelligences perhaps that we've created are talking about and interested in, because that's just way beyond us. So it's about participating rather than standing by. For me, that's where sim fits into the singularity. Although I myself have some issues with the term singularity, because it seems like it gives this idea that overnight suddenly there's going to be enormous changes and we won't be able to predict what's going on. And that, there's something about that could happen. It's sort of possible and plausible, and there are several authors also in that book that describe that. But then there are many other scenarios, and we have to remember that we're talking about a universe with physical laws, so everything has resource requirements, which means that a sudden overnight takeoff that leaves us all in the dust is kind of unlikely, because how fast can you reorganize all those physical resources? So I have some issues with the concept of the singularity as this sort of actual singularity, this takeoff phenomenon that at some point becomes just really, really, really fast.
So you think it's more likely to be what Werner Vinge calls soft takeoff rather than a hard takeoff?
Yeah, I'm kind of more of a soft takeoff person, because I think you run into some physical limits there in terms of how the rate at which you can keep changing stuff. Mm-hmm. Now, if you were just a bystander, then at some point it might begin to seem like a hard takeoff situation, because what's going on around you is no longer involving your participation at all. They can acquire their own resources and whatever. But if you aren't, if you're a participant, then I think it'll remain a soft takeoff rather than a hard takeoff.
Yeah, I think Marvin Minsky famously said that if you're riding the wave, there is no singularity.
That's a really good term. I hadn't heard that yet, and I'll try to remember that one. If you're riding the wave, then there's no singularity. Okay.
Yeah. Because that's what allegedly he supposedly intended to do. Now, I don't know how successful he is on that front, but at least the idea I also like very much, that if you are riding that wave like a surfer, then there's no singularity at all.
Yep. That kind of summarizes what I'm trying to say. It's perfect.
So what are the chances of us surviving such an event if we don't take the active role? What are the chances of us taking the active role and being a surfer and surviving, or not doing anything and then ended up bystanders that are left, in the dustbin of history, perhaps?
If we never take an active role, if we basically stay who we are and we just hope that maybe what we create takes us along, I think our chances long-term are very low. Because, how much do we really care about what's going on with ant colonies and stuff like that? It doesn't make much sense to think that we would be very significant and somehow move on. I think our chances long-term would be low, especially since long-term, even our solar system's not staying the way it is. Mm-hmm. So why would everything stay okay? Short-term, that depends on the type of takeoff, on controls, on resource regulations, all sorts of stuff. I'm sure there's so many scenarios, and I really don't know what to predict. It's too confusing.
Well, Randall, it's about time we bring our interview to an end. But before that, I have the last two questions that I traditionally ask of all my guests. And the first one is, where can our viewers and listeners go and find more about you and your work?
They can certainly go to the website carboncopies.org. That's the main site from which you can find links to everything else, to our Facebook group where we do ongoing discussions of things and events that are coming up. It's also the place where we collect resources and references, and that also points to things like my personal website, which is rak.minduploading.org. That's the best place to start. From there, you'll find everything else.
And the last question that I always ask is this: do you have a single message that you would like our viewers and listeners to take away from this interview today? If there's one thing that they need to take away, what would you like that to be?
Okay. The most important thing to take from this is that when we talk about substrate-independent minds, and especially the approach called whole brain emulation, this is a very concrete thing. It's an actual set of scientific projects and development projects based on our current understanding of neuroscience and the engineering that we have available. It's not science fiction. This is stuff that's being worked on right now, and so you should pay attention to that. That's basically my message.
Fantastic. Dr. Randal Koene, thank you very much for being on Singularity One-on-One today.
Thank you.